Hello, welcome to this course. This is EE603 Digital Signal Processing and its Applications. My name is Kumar Appaya and I will be your instructor for this course. So, at the outset, let me take this opportunity to welcome all the new students to IIT Bombay, the new MTech PhD students who actually have got admitted this semester, but unfortunately, you have not been able to come here in person. I promise you that soon we all would like to have you here and get the full experience of our campus, the Mumbai weather, all the good things that come with being a student of IIT Bombay. For the current semester though, we will be conducting this course through the online mode. For those of our students who are already admitted but are also at home and listening into this course, welcome back to this fall semester. We hope that with our efforts we will be able to do as much justice to this course as we would have if you had been present in campus in person. So let me start with an introduction to this course. This course is on digital signal processing and its applications. It's a graduate level course. The course code is 603. The basic prerequisite is signals and systems. So some knowledge of LTI systems, Fourier transforms, and that is what it has. Now to the important question, who should do this course? Why should you do this course? Let me first start with why you should be doing this course. So in this course, we are going to be dealing with the aspects of signal processing that are largely connected with discrete time systems. If you recall, in signals and systems, you were focusing on what a signal is, how you can model a signal, what are frequency components, and so on. In this course, we are going to not look at x of t, but x of n. That is, we are going to look at sequences which are indexed by integers as opposed to real numbers. Now this surprisingly is not that limiting, because a large number of signals which occur naturally or in man-made systems can be captured within this framework. For example, every time you make a phone call, or if you are recording a speech like I am, the data is to be stored or transmitted using bits or digitized transmission schemes. Whenever that is the case, the continuous waveform is always broken into chunks and is always indexed by xn. Now the testimony to the fact that this can be made to work is the fact that you are able to listen to this, or you are able to talk to your friends on the phone without really noticing that this discretization has taken place. But what is the key advantage of using this discrete approach? The key approach is that you can use computers, or in our particular domain, digital signal processors, to perform various enhancements to the signal. And these enhancements and improvisations are key in enabling effective transmission of the information. To give you an example, if you look at the transmission of an analog signal over a medium such as a wireless medium, you will find that there is a lot of distortion which can occur, and to transmit the signal faithfully over long distances is difficult. However, if we convert this problem to one of bits or using digital systems, it is much easier. However, this does come at a cost. So what are the trade-offs when using digital systems, or what are the trade-offs when using digital signal processing systems, and can these digital signal processing systems capture the waveform that you want or capture the image that you want? These are some questions that we will be looking at. In terms of applications, there are too many to name. As an example, we have been talking about speech. whenever you listen to music, such as your MP3 or wave files, OGG, all these formats, or if you talk about image or video, these are all largely captured by digital signal processing. And offshoots of this course, for example, once you do this course, you will be able to understand these systems better. In addition, if you think about it, not all signals are these images, photos. For example, many man-made signals fall into this category. Take, for example, a stock price. Okay, stock prices are available at certain ticks, and they are naturally discrete. Okay, because they are reported once every second or once every minute. Measurements of temperature measured once every second or minute, or measurements of rainfall if you are in a place where you have monsoons, they are also agglomerated over certain time intervals. All these will be in our ambit of signals, and capturing information about all of these, making a sense of what these are, understanding these, or enhancing signals, such as if your microphone picks up a lot of noise, can you do some enhancement of the signal? These are some things that we will be looking at. Let me just show you, give you a brief introduction to what we are going to cover in this semester. So, yes, as I mentioned, we are going to do it in the online mode, but this course will be highly interactive and student participation is a must. Just to give you some perspective, we are going to offer recorded lectures along with at least an hour of interaction with you every week, wherein I expect you to ask me questions, understand the concepts better, to get your doubts clarified. To drive home the concepts better, I am going to issue regular homeworks which I expect you all to solve independently. We will largely try to use Python for it. Python and the ecosystem around Python has a lot of tools that will allow you to learn signal processing effectively. I will offer you some guidance on how you can use Python in order to solve your homeworks and learn a lot more about it. And as I mentioned, please note the instructor details. I will post this on Moodle. I will also announce office hours which are specifically for you to contact me for doubt clearing, and I will also list the names of the TAs who are very experienced and very good students who are going to help you throughout this semester. So let me summarize the course contents. We will spend the initial part reviewing the concepts of signals, systems, and Fourier transforms and Fourier series. Some of these are things that you would have studied as preparation for your entrance exams or in your undergraduate curriculum. But we are going to start in earnest with sampling. That is, we are going to explore the relationship between discrete time signals and continuous time signals. We are then going to delve deep into our understanding of discrete time signals and systems. These discrete time signals and systems are going to be the crux of this course, and understanding their properties, how you can analyze, how you can design them, is going to be an important part. We are then going to look at the Fourier transform analog in the digital signal processing domain, that is the discrete time Fourier transform, and we will then mention Z transform and see how these tools tie in with analyzing and understanding more about digital signal processing systems. We will then discuss the discrete Fourier transform and the FFT algorithm, what its importance is, what it computes, and how you can understand it. And then we will touch upon the design of digital filters for various applications, for example for noise reduction, for speech enhancement and things of that sort. And finally, we are going to talk about various applications such as image compression, communication applications such as orthogonal frequency division multiplexing, and more. Like I mentioned, much of these will be material which you are going to have to see, discuss with me, solve problems which I will give you, solve assignments, and learn. So one key aspect that I would like you to not forget is that you have to learn very well, because this is going to lay a foundation for you to do well in all other courses or in your job or whatever it is, because DSP is among the most fundamental topics for electrical engineers. Finally, I will mention about who should be doing this course. So it is typically considered that only people who are interested in signal processing and communications need digital signal processing. This is not true. Everybody who has any application which is related to signals should study digital signal processing. For example, if you take a UPS, that is a universal power supply, uninterrupted power supply, which is designed to automatically switch on when the power cut happens. A UPS is actually, if you read the label, called a sine wave inverter. Okay. So typically there is a digital signal processor which controls the aspect of taking the power stored in a lead acid battery and converting it to an alternating current waveform. So a UPS necessarily has a digital signal processing system inside it most of the time. So power system, people who are doing power systems will find use in DSP. Then what about people who are into microelectronics and circuits? Typically, people who are into microelectronics, circuits and VLSI often end up implementing systems for data conversion, for broadband communication, or for just transmitting signals in a high frequency board, things of that sort. In all of these situations, the likely application is a transmission of a digital signal. Understanding the dynamics of how the digital signal is affected when you design and implement these let's say VLSI devices, waveguides, microstrips, all these fall under the ambit of digital signal processing. So as an electrical engineer or an engineer in general, this fills some of the gaps which you may encounter in other topics. So given that this is the case, all engineers and all electrical engineers will find some benefit from doing this course. Please check Moodle for some more information about this course, and I hope to have a good semester where you are able to learn very effectively through this course. Thank you.